Number 18, we can see that we have multiplication. We can see that this is not going to work with substitution, nor is this a known integral. So we're going to try to apply integration by parts. So I have the formula up here, and the formula is just a rearrangement of original integral u dv into a new expression that has a different integral v du. And hopefully that v du can be integrated. So in this case here, we're going to select the dv as the most complex term we're able to integrate. So in this case, we can't integrate log, so we're going to use x dx. So dv is our x dx. We're going to integrate this and end up with x squared over 2 as our v. Our u is going to be log of x plus 1. So our du works out to be 1 over x plus 1 dx. Okay, so rearranging this new integral is going to be our uv. So we end up with our x squared over 2 log of x plus 1 minus the new integral. The new integral is v du. So I'm going to take the 1/2 out. So I'm going to have 1/2 x squared, v du. So it's going to be x squared over, the du is going to be 1 over x plus 1, so x squared over x plus 1 dx. Okay. Now this one, the new integral, unfortunately, still cannot be integrated. However, this one we can try a unique substitution in this. So the substitution is going to look like this. And this is not a very common substitution, but I'm going to let my u equal to x plus 1. And what it means is that the du is the same as dx. So I can just replace my u's and my x's and do this in terms of u's. Now, what's the advantage of doing this? So let me just write this first part out. We have x squared over 2 log of x plus 1 minus 1/2 log. Now, the advantage of doing this is when I do the substitution, I now have the monomial term in the denominator. That allows me to distribute that monomial term into the numerator. So in this case, x squared becomes u. Instead of x, I'm going to do x is equal to u minus 1. And then replacing that x with u minus 1, I end up with u minus 1 squared. The dx I can replace with a du. And this just becomes an integral in terms of u, but the difference is that instead of binomial x plus 1 in the denominator, we get a monomial term u in the denominator. And that allows us to then isolate the powers, to use power rules. So it looks like this. X squared over 2 log of x plus 1 minus 1/2. And when I work this out, I'm going to end up with u squared minus 2u plus 1 all over u. And that we can then separate the powers. We end up with u, no power, just minus 2, and then a plus 1 over u. Okay, so my expression looks like this. Log x plus 1 minus 1/2. My integral then now becomes u squared divided by u, that's just u, minus 2 plus 1 over u du. All those terms can be anti-differentiated. So we end up with x squared over 2 log x plus 1 minus 1/2. And this can be anti-differentiated into u squared over 2 minus 2u plus log u plus c. Okay, so that plus c is not just on that, but on the whole, it can be the plus c for the whole expression. And then I can simplify and substitute back my x expression. So I get x squared over 2 log x plus 1 minus, and this becomes u squared over 4. So the u I'm going to replace back with my x plus 1 minus, so it's going to be negative 1/2 times negative 2, which is plus u. Okay, so that u is really x plus 1, and then plus log u. So it's going to be, minus 1/2 log u, and the u I'm going to replace with that x plus 1. Okay, so there's my new antiderivative. If there are like terms, I should combine them. In this case, there doesn't seem to be terms that can be combined very easily, so we're going to leave our final answer like that.